Okay. Good morning and welcome to week 7, everyone. We started sets last week, and that's what we're going to continue to study today. We start with ordered intervals, which actually, again, as you would have noticed by now, that every lecture I start with what we did in the previous lecture. Right? So in the previous lecture, we talk about sets. Some well-known sets and Cartesian product of sets, not that much, but I'm going to do that again. What is a set? Set is just a collection of objects. So collection doesn't matter, you can rearrange them, put them in different order and whatever you like. But then there are ordered sets. Ordered sets are where the positioning matters. Right? For example, placeholders. What position 1, 2, 3 does matter. Sequence of months in a year, that also matters, things like that. So what is ordered interval? As I said, with sets, the ordering of elements in the set does not matter. If you put 1, 4, 3, it's the same as 3, 4, 1. Yeah. Sometimes order does matter though. An ordered pair of elements, we put them in these small brackets. That means these are ordered pairs. Okay? This A and B is an ordered pair. If you put B, A, then they are not the same. So please keep that in mind. In the small bracket, if you change their ordering, then the sets are different. Okay? In here, if within curly brackets, you can switch them around, it's fine. So similarly, an ordered n-tuple would be n elements in ordered form. 1, 4, 3 is an ordered 3-tuple, and 1, 4, 3 is not the same as 3, 4, 1. When it's in the small brackets, as I said, order does matter, so we have to have them in fixed order. However, if you put them in curly brackets, then it's the same. Make sense? All right. What's a Cartesian product? Cartesian product actually is not actual product that you consider. Like 2 times 3 is 6. No, it's not that. By Cartesian product, it's from René Descartes. He was a famous philosopher and mathematician. Well, Cartesian product is that you pick one element from the first set, cross second element from the second set. Right? That is the list of all the possible orders. It's not the cross. It's not the product itself as a multiplication. So A cross B means ordering of all those elements coming from A and the elements coming from B. When we say x comma y, where x is in A, y is in B, that means it's a set. Remember, within curly brackets, it's a set. It's a set of all those x and y's. So that means this would be something like x1, y1, one element, x2, y2, another element, so on. That kind of many elements. So the first one coming from A, second one coming from B. As an example, if A is a set of digits from 0 to 9, yeah, and B is a set of letters from A to Z, then 3 belongs to A, T belongs to B, so this is an element in A cross B. So A cross B is a bigger collection of elements. Does it make sense, everyone? Do you know how many elements altogether would be in A cross B?
260.
Anyone defer to disagree? Anyone disagree with that claim? 260 elements, indeed, because there are 10 digits here, and there are 26 alphabets, right? 10 times 26 is 260. Yeah. There are 260 elements altogether. Now, m comma 7 is not in A cross B. it is in B cross A. Now, if C is GHI and D is 4, 6, then C cross D would be G4, G6, H4, H6, I4, I6. All the possible ordering combinations. First one has to come from C and second one has to come from D. And all the distinct ones here. Now the C and D as above, find D cross C and D cross D. So, yeah, maybe you guys do that. Can you do that please, quickly? D cross C would have 6 elements. This is one element, 4 comma G in small brackets is one element. Okay. Now this is one object, 4 is coming from D and G is coming from C, then 6 is coming from D and G is coming from C, up to so on. So altogether that would have 6 elements, 2 from D, 3 from C, so 2 times 3 is 6. So overall 6 number of elements, D cross D would have 4 elements similarly. Any questions, anyone? So Cartesian product of more than 2 sets, the process is exactly the same. If you multiply 2 sets or cross product of 2 sets or cross product of 3 sets, very similar. You would have order triple or order n tuples and all that. Now, a car registration number such as KCT 454 can be regarded as an ordered 6 tuple. So you can write this KCT 454 as K, C, T, 454. Yeah, and these come from sets L, 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 where L are alphabets, all of them. D, D, D are digits from 0 to 9. Now, how many combinations in L cube, D cube altogether? So do you know the number of combinations would be 26 cube times 10 cube, yeah? So that many registration numbers can be generated from these sets. Yeah, this is just an example that how these things work. Cartesian product of a set with itself. For ease of notation, I already described that if I'm taking cross product of A cross A, we write it A square. That means set is taken a cross product with itself. It's not actual multiplication, as I said. So A square would be 3, 3, 3C, C3, and CC. Now, some examples. If B is 2, 4, 5, as you can see here now, B is a set, and it's written in curly brackets. It's not an ordered triple. Then 4, 4, 2, 4, 4, 2. 4 is the first element in an ordered triple. So 4 comes from B. Next 4 is also coming from B, and 2 is coming from B again. So that ordered triple belongs to B cross B cross B. So this belongs to belongs to or is an element of B times B times B, because this 4 is from B, that 4 is also from B, and this 2 is also from B. So that's why we write it as B cube. And similarly, 2, 4, 2, 5 is in B4. Every element is in B, right? So when you put that in quadruple form, right, put them together, that belongs to B4. Is that right, everyone? So these are just some examples. You can look at them later. So very trivial examples. Already gone through a few of them. Okay, what's the Cartesian plane? Now we come to the main point here. Now, look, you would have done this in at school, geometry, Cartesian geometry. What do you mean by that? We mean you normally write this axis as x and that axis as y. Is that right? Yes? So now, this is actually x, Cartesian product with y. Whatever graph you are taking is actually a Cartesian product. This plane is a Cartesian product of this line x with that line y. So normally you probably call that as r, real numbers. Did you call that r, or did you call that x, or what did you do? Do you remember? What was impatient? It doesn't matter. Whatever you have here, you take a cross product, right? So what you're going to get? This is a plane that has combinations A, B, such that A is coming from R and B is also coming from R. What does this mean? This is a collection of all those pairs, A, B. For example, this, when x is 0, y is 0, so it has 0, 0 in it. 1, 1, so this point is 1, 1, 1, 1 also in it. Yeah. Then similarly, you can have half and 1/4. This is 1/2, that is 1/4. So this point, which you call that 0.5 and 0.25, is also in it. Then you can think of somewhere here 10, 1 is also in it. Yeah. So it's a collection of all such kind of pairs. It's called Cartesian plane. Right? Now, on this Cartesian plane, you can talk about a particular path, a particular track, a particular direction. If you take a particular direction, then the graph would be slightly different. For instance, you may want to talk about ordered pairs which are of this form: 0, 0, 1, 1, 2, 2, 3, 3, so on. Do you know what that graph is? Exactly. So it is 0, 0, 1, 1, 2, 2, so on. Yeah. So here I talk about every possible pairs, then it is this entire plane. Yeah? Every point on it. Here I talk about just one line. particular ordering. Within curly brackets, it doesn't matter I write 1, 1 first or 0, 0. It's my choice. But within these small brackets, I don't have a choice. Specifically here, in that set. Here they are the same, so it does not matter. So this is called your Cartesian plane. So R2 is a set of all ordered pairs XY. So geometrically, this looks like as a two-dimensional plane where each point is sort of this kind of a dot. So what does Cartesian mean? Cartesian plane are named after René Descartes, a French mathematician and philosopher. Cartesian is the Latinized name. Yeah. Anyway, in this book, 1637, Descartes applied algebra to geometry. From these ideas, we are now familiar with Cartesian geometry. All the geometry that we do, make pictures, graphs and all that, that's Cartesian geometry that we deal with. There are many other kinds of geometries as well, but we don't use them that much. I like this quote, I think, therefore I am. You don't think, you're gone. Nobody cares. This is also interesting. Descartes suffered poor health when young, so until the last year of his life, he remained in bed until 11 a.m. each day. Then he had to change his routine. In 1649, he went to work for Queen Christina of Sweden. The Queen wanted to draw tangents at 5 a.m. So Descartes broke his lifetime habit of getting up at 11 o'clock. So after only a few months of walking to the palace in the cold Swedish climate, he died with pneumonia. So lifetime habits actually matters a lot sometimes. I remember those times, buildings were not that much, friendly. I would say insulated and all that. So things happened. There was another guy, Ramanujan, he died very similarly in England. He was a great mathematician, but couldn't adjust in that climate. Anyway, now we talk about, so far what we talk about? We just talk about what we mean by Cartesian product. Okay? By Cartesian product, we mean sets where one element coming from one set, another element coming from another set. That's the cross product, right? And when we write them in ordered form. Now we talk about computer representation of sets. Okay, we'll now look at how computers store and manipulate sets. They would, of course, do in 0 and 1s form. Do you agree with that? Okay. Now we're going to find a way that if you are given two sets, right, how their intersection, union would work. And how these would be stored and manipulated in sets. So to enable computers to handle sets, there needs to be a definite order for elements. So we need to have definite ordering of elements, okay, of the universal set. If it has n elements, any set A is represented by a string of n bits. The ith bit is 1 if the ith element of the universal set is in the set, and 0 otherwise. What that means is, let me put that some example. Suppose your universal set is A, B, C, D, E, F, G. That's your universal set. Okay? And then you have a set A, which is D, F, A, G. Right? Remember, it does not matter within curly brackets how these sets are written, right? The elements could be rearranged. It's your choice. If it's ordered form, then you can't do that. But if it's in the curly brackets, you can do that. So the first step that you do, A, you can write it as A, D, F, G, right? Okay. So first thing is to find its bit representation. From the definition, if the element is in the from the universal set, if it's there, then I would write as 1, otherwise 0. So A is there, so I have 1, B is not here, C is not here, but D is here, E is not here, F is here, and G is here, and that is my bit representation of set A. Make sense? Right? Yes. You have universal set. Okay. It has bit string, whatever. Now, if I want to write A in bits, now A is a sub-collection of that. So I have to identify in some way. If the element of A, so here you look at the elements of A. So whatever are missing from the universal set, I mean from the set A which are in universal but not here, you put 0 string there, 0 bit there, otherwise 1. Okay, A is here, so I would put 1. Since B and C are missing, I would put 0, 0. Now here you can see that ordering matters here now. Because I have to look for how these elements are in the universal set. Okay, let's look at more examples. So for A, what we got? We got 1, 0, 0, 1, 0, 1, 1. Yeah? Okay. Now, similarly, now look for here. This is the bit string of B. What the set B would be? So B would be equals to, A is not there, so I won't write it. So this is missing, means A is missing. Then B, C, D are there. E is missing, F is there, and G is there. Yeah. All right. So that is going to be B, C, D, F, G. Yeah. So this is how these are basically stored. Now we have to look for how these are manipulated, how these are operated. If I'm going to look at the intersection or union or complement operations, then how these would work in the bit streams. So for sets with the same universal set, the operations of union, intersection, and complement can be carried out directly on the bit strings without having to convert to the original set. So we don't really need to convert them to original set. If we are given bits, then yeah, done, basically. How that process would work, that we don't have to invoke to original set. With intersection and union, for instance, if you're calculating intersection of two sets A and B, you put their strings on top of each other. If both of them are 1, it's 1, otherwise 0. That's your intersection. Union would be if any of them is true, that is 1, then it's true, otherwise it's false. So exactly the same way as you did logic, but now we are putting strings on top of each other. Let me give you examples. It would be clear in example. Find the bit strings of A intersection B. If A has a bit string, so this is A's bit string, first one. Then you have B. B is 1, 1, 1, 1, 0, 0, 1, 0, 0, 1. So I have put these bit strings on top of each other. If I'm calculating intersection, so I want to calculate A intersection B, right? If both the strings are 1, then it is 1, otherwise 0. So remember, false and true is false, so this would be 0. 1, 1 is 1, 1, 1 is 1. If both the strings are 1, then it is 1, otherwise 0. So then you have 0, 0, 0, 0, 0, 0, 1. So this is your A intersection B. Yeah? Do you understand that, everyone? Now look at A union B. If any of them is 1, then it is 1. Okay? What that means, we would have 1, 1, 1, 1, 1, 1, 1, 1, 0, 1. There is only one possibility where both are false. This is this. All others, one of them has 1 at least. So in a union case, it's like true or false is true. True or true is true. So the only case it could go to false is if false or false, then it's false. Otherwise, there is no possibility. Agree? Everyone? Now, what do you think the complement would be then? If I want to calculate what A complement is, what that would be? Exactly, you just switch them. So if you, A complement would be opposite to this, which would be 1, 0, 0, 1, 0, 0, 1, 0, 1, 0. So this 0 becomes 1, that 1 becomes 0, that 1 becomes 0, this 0 becomes 1, so on. So that's your complement. Now, from this you can see that dealing with intersections in bitwise operations is extremely easy. It's not that difficult for computers to handle. You know what is yesterday's big breakthrough? There's yesterday's breakthrough that took 54 years, actually, for scientists to discover. X cubed plus Y cubed plus Z cubed is equal to some number K, and K is between 1 and 100. For what value of X, Y, Z as positive integers this will hold? And after 54 years of work, they figured out there is only one number when K is 42. X, Y, and Z are humongous numbers, very big, I don't remember. So very big integers is equals to 42. It took them millions of hours of supercomputer computing power to do this. 54 years. What's that? They could have just read that each other started in galaxy. Yeah, they did. They did. Actually, they used it. They actually borrowed server powers from many places to did that. Yeah. Anyway, that was something happened yesterday. Now, the point I'm making is, I just want to identify that how complex things are. If I similarly instead of Q, I would write 4 and ask very similar question. Oh, that would be more challenge, right? But lots of things, lots of challenging open problems, heaps of them. Yeah, if you think ever that human curiosity would end, never. No. The growth would be exponential. The way it is, the way we are now at the moment, every now and then you see some kind of new technology. You see some kind of, from room-sized computers to we have moved on to very, very tiny-sized computers with more power than room-sized computers, Yeah. So human curiosity doesn't stop. It will just keep evolving. Problems keep arising, and it's our duty to just keep solving them. Anyway, so some questions I have done here. We look at more bitwise operations. These work same as OR and NOT operations. Complement, we just did an example. Now, can we do these questions, please? Obtain the bit strings of A union B A bar, A complement, A union B, intersection A complement, if A has bit strings this, B has bit strings that. Can you just practice that for me? Here. Okay, I'm sure you will have done that now. I'm looking for A union B, where this is 1, 1, 1, 1, 0, 0, 1, 0, 0, 1. Yeah, so I want to do A union B. That would be 1, 0. Oh, no. Actually, I've done that probably. Yeah. So I would have 1, 1, 1, 1, 1, 1, 1, 1, 0, 1. For A union B, A complement would be 1, 0, 0, 1, 0, 0, 1, 0, 1, 0. And A union B intersection A complement, I would put that here. A union B intersection A complement. So I put that 1, 0, 0, 1, 0, 0, 1, 0, 1, 0. So I would have 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Is that the one you got? Okay. If not, then there must be some calculation errors then. Anyway, that's a bit of a practice. You can compare your answers here. So I got the same. So application of set theory. Where do we use them? Let's look at some examples. In 1970, Dr. Edgar F. Codd of IBM introduced the relational data model as a theory for database design. Okay. Codd developed his model by applying mathematical set theory to database design. The model was soon expanded and refined and rapidly became the main focus of practically all research and development in databases. What you're going to do, you're going to study this in second year IT subject, CSE 2 DBF, if you have not done that already. I'm not sure, because since we have done sets now, I think you study this next year at some stage. Yeah, this subject. Whatever topic we are doing, it has applications in the study that you're going to do. Okay, there is nothing for mathematics purpose that we are doing, for mathematics as a discipline. All the topics that we group together would help you in your IT degree. Yeah. Let's look at some binary relations. We'll stress a little bit more on this actually soon. Let's start. A binary relation occurs when we compare, when we say something about a property of an object relative to another object of the same type. Binary means two, so we are trying to compare two objects. So one object could be taller than the other object. One object could be, similar characteristics. The statement Sue is taller than John. Now you're comparing two objects here. It's a binary relation. So first we do a relation. Then we're going to study specific type of relations. Then we're going to study, we're going to divide those relations into sort of partitioning into very small characterizations. We really want to understand relations from mathematics perspective. Here are examples of statements from everyday life which illustrates relations. Robert is the husband of Mary. It's a relation. Mary is sister of Jane. Victoria has a border with New South Wales. Australia has a smaller population than China. What do you observe in all of these examples? Ordering matters here. If I say Mary is the husband of Robert, that would be wrong. If I would say China has smaller population than Australia, it would be wrong. So ordering matters there, in all of these relations. Mary is the sister of Jane. Ordering does not matter there. Jane is the sister of Mary. Okay. Similarly, if you change that as a sibling, it's fine. It's okay. So from each statement, we have to first find out whether ordering matters or not. Here are examples of statements from mathematics and logic which illustrate relations. 12 is greater than 4. Is a relation. Greater than is a relation here. This does not matter. These numbers does not matter. 12 is greater than. Greater than is a relation. Okay. P is logically equivalent to not P. Is a relation. A is a subset of A, B, C. It's true. It's a relation. Subset is a relation. 20 is divisible by 4. Divisible by here, this word divisible by, it demonstrates, it characterizes a relation. It gives us a relation there, okay? Line L1 is parallel to line L2. Two parallel lines, basically. Here, ordering does not matter. In this case, ordering does not matter. So parallel to is the relation. So if line L1 is parallel to L2, that means L2 is parallel to L1 as well. So these are different examples. Some of them ordering matters, some of them ordering does not matter. So we're going to look at deeply into these relations in the next lecture, and we find out their properties. Properties may well be whether when I say that a relation is transitive. By transitive, I mean if I'm related to one object and that object is related to another object, then in other words, I'm related to that object C. That's called transitivity. If you say that A divides B and B divides C, that means A divides C. Things like that. Yeah? If I'm a brother of John and John is a brother of, let's say, Alpha, so in other words, I'm a brother of Alpha. So this is called transitivity. Similarly, there are reflexive, irreflexive, symmetric, antisymmetric, transitive. There are specific types of relations that we want to study, and based on that relations, we want to characterize objects. So some comments. In each of examples, a statement is made about a pair of objects of the same type. Okay? Same type objects, then we are comparing. If the objects are different and there is no characteristics common, there is no point to compare them. Right? The order of objects is often important. For example, while it is true that Australia has smaller population than China, it is not true that China has smaller population than Australia. Do you know how many times Chinese population is more than Australian population? Less. What? 20 times? We are 23 million here. And they are 1.4 billion. Now, how many times? Come on. 1,400 million is 1.4 billion. You simply have to divide with 23. You're talking about nearly 67 times. Yeah. Something like that. That's quite big. It's very big. Anyway, as the relations involve two objects of the same type, where order is important, so we are dealing with ordered pairs. This leads to a more formal definition of the term relation. Now, the more formal definition is, a relation is a statement about ordered pairs X, Y that are in the set A cross A. You know, when you're comparing two similar kind of objects, that means you're taking a subset of A cross A. Cross, when I say, is Cartesian product. The statement is either true or false for each pair. So either X is related to Y or X is not related to Y. Only one of them is true. Okay. Either you have a birthday in the same month as anyone else in the room, or not. Yeah? So there is only one of them is true. It's not possible that both the statements are true. It won't happen. So binary means here we will deal with only one of the true statements. Any questions? So we'll do these relations in detail in the next lecture. We'll look at their properties, systematic properties, and if satisfied, then we call these relations particular name we give them. We'll call them, for example, I can tell you now, we call them equivalence relations. And then after that, once we have done equivalence relations, we'll do the partial ordered sets. Which would be, again, we have, for example, if you want to characterize all the cities or all the cars registrations or things like that, how relations would help to characterize them, right, or list them in proper ordering. That's what we're going to do, probably in the next 2-3 lectures. All right. Have a good day, everyone.